Number 28, lactic acid have this structure. So what properties does it have? A, decolorizes aqueous bromine rapidly. It is unable to do that as it doesn't have the alkenes CC double bonds. Insoluble in water. Now lactic acid is a small organic molecule with groups that are able to form hydrogen bonds with water. Groups like your carboxyl group and your hydroxyl group. So small molecules and able to form hydrogen bonds, it should be soluble in water. It reduces Felling's reagent. It does not have any aldehyde groups, so it will not be able to reduce Felling's reagent. So D is the answer. Two molecules react with each other in the presence of a strong acid. How can you do that? If I have another lactic acid, we have the hydroxyl group that can join to the carboxyl group through esterification. So your acidic group here will also be able to join to your hydroxyl group by esterification. So with sulfuric acid concentrated, two molecules can undergo reaction to form esters or form ester bonds. Citric acid, what is the volume of sodium hydroxide required to neutralize it? First of all, you have to figure out that citric acid can produce 3 moles of H plus per mole of citric acid. It has 3 carboxyl groups. So the ratio of citric acid, you will need 3 times the number of moles of sodium hydroxide, because sodium hydroxide can only produce 1 mole of hydroxides. So if we have 0.005 moles of citric acid, you will need 0.00 or 3 times the amount, 0.015. Volume of sodium hydroxide, moles over concentration, you have this amount, this volume in dm cube, convert to cubic centimeter. Number 30, we have this molecule that is heated in hot sodium hydroxide. So the bonds here, your ester bonds will be broken, your amide bonds will be broken here, and we end up with a small molecule that comes out, right, and the large molecules on this end. So focusing on a small molecule, if we were to reconstruct it, it might look like this, with your amine groups and your carboxyl groups, right, but this is not the final result. We have to check that and realize that it is under sodium hydroxide environment, alkaline environment. This is a basic group, so no changes to this. For this is an acidic group. Under sodium hydroxide, it will form a salt. So this is our final product, okay, which is our option B. Phosphide and ion and chloride ions. The number of protons you should be able to obtain from the periodic table. So 15 and 18. Electrons, they will have 18 for both. Neutrons, 16 and 18. So only option or statement 1 is correct. (32) Aluminum chloride, Al2Cl6. Right, the molecule looks like this. There is a dative bond here. Arrow is drawn incorrectly. It should point to be aluminum. Right, chloride is a donator. but nonetheless it's still a covalent bond. So when we say it sublimes easily, we are saying that it goes from Al2Cl6 solid to Al2Cl6 gases readily. So what we are breaking is not any of these bonds here. Right, these bonds remain intact during sublimation. It's the bond between one molecule to another molecule. So the intermolecular bonds are weak. The coordinate bonds, covalent bonds are unaffected during sublimation. Number 33. Which statements are correct for all exothermic reactions? For all exothermic reactions, the enthalpy change is negative. Statement 1 is correct. The pathway diagram products are shown lower than reactants. So that also means that the enthalpy change is negative. So statements 1 and 2 are related. Reaction will happen spontaneously. This is not necessarily always true. It depends on the activation energy. Right? If the activation energy is very high or high, the reaction will require an external energy. Right? So statement 3 is not always correct. Which of these reactions are redox reactions? The most convenient way to do this is actually to pick one atom and compare it to the products. Right? You don't have to check all the oxidation states. So for example, nitrogen, I choose this one, +2, and then 0 at the end. There is a change, so for sure it's a redox reaction. Sulfur, +4, +6. There is a change, it is a redox reaction. For the last statement, sulfur is +6, and in sulfuric acid it is also +6. So there's no change. It's likely not to be a redox, but if you are worried that you have chosen the wrong atom to compare, you can do a quick check for the others. Each oxygen is -2. Notice I'm just counting each oxygen, not the total. -2 oxygen, -2 at the end also. No change for oxygen. Hydrogen, each one is +1. At the end, each one is still +1. So right, this confirms that statement 3 is not a redox reaction. 35. Which one will cause a change in pH when added to water? Silicon dioxide, silicon 4 oxide, although it's acidic in nature, it is actually insoluble. So you have to be careful. When added to water, it doesn't dissolve. There will be no change in pH. Calcium oxide will react to form calcium hydroxide. The pH will increase, turns the solution alkaline. Sulfur dioxide is an acidic gas. It will dissolve to form sulfurous acid, and then that will release H+ ions. So the pH will decrease. So 2 and 3 are correct. (36) You require some background knowledge on the uses of halogenated hydrocarbons. So they can be used as solvents. For example, we have our CH-Cl3, this is chloroform, tetrachloromethane, and many more. Refrigerants, for some most famous example will be our CFCs, chlorofluorocarbons. Monomers in polymer manufacture. We can use vinyl chloride to form PVCs. So all three are possible uses for halogenated hydrocarbons. (37) Which structures to the 4 carbon atoms lie on the same plane? One way you can do it is you have to check the connecting carbons. Right, that means carbons, besides the carbons at the end, do they have sp3 or sp2? If it's sp3, then the 4 carbons will not lie on a plane. If it's sp2, then yes, the carbons lie on a plane. So okay, using this example, the connecting carbons will be these two. This carbon is sp2. This carbon is also sp2. So your carbons all lie on a plane. Option 2, the connecting carbon is here. Right, these are the carbons at the tail end. So we just focus on this carbon, sp2. So lies on a plane for the rest. Option 3, this carbon is the connecting carbon. This carbon is sp3. Alright, yes, 4 single bonds. The hydrogen is not explicitly drawn. So since this connecting carbon is sp3, these carbons will not lie on a plane. It's tetrahedral angles to each other, 109.5. So option 3 is out. Number 38. Statements of 2-butyl butanol 1-ol. Number 1, it can give HCl with reaction with PCl5. Reaction with PCl5, the chlorine will replace the OH and we will get HCl produced, fumes. So statement 1 is correct. It can be oxidized to form aldehyde. This is a primary alcohol, so it can be oxidized and distilled to form an aldehyde, right, using dichromate, acidified dichromate. 2 optically active forms. There is a chiral carbon here, so it can have optical isomers. Propanone and hydrogen cyanide. So first statement, cyanide is an electrophile. That is incorrect. Cyanide has this lone pair here. It will be attracted to a partially positive carbon. The carbon is partially positive because of the electronegative oxygen. So what happens, or what is actually happening, is cyanide is a nucleophile. It looks for positive regions. Statement 1 is wrong. So statement 2 and 3 must be correct. Okay. It is an addition reaction because overall, if you have a propanone and your hydrogen cyanide, the final product you get will be here, one single molecule. So addition reaction. Heterolytic bond breaking is involved. Heterolytic bond breaking, if you focus on this one, both of the electrons are passed to your cyanide. Right, so that's your heterolytic bond breaking. Mono potassium citrate. This molecule. Which statements are correct? It does not have a chiral carbon. Okay, if you look at all the carbons here, this carbon is joined to 2 hydrogen, so it can't be chiral. This carbon is joined to 2 identical groups also. Right, the top group and the bottom group are the same, are identical. So this is also not considered chiral carbon. So we do not have any carbons joined to 4 different groups here. Dibasic acid means it releases 2 H+ ions per molecule. One from here, and one from the top. So statement 2 is correct. And the acidic group allows it to react with hydrogen carbonate to give carbon dioxide.